I'm not that bad. That's the hockey player that has the same name as I do. He stole my name.
He's older than you.
You're spelled wrong. Come on. No. A-Y.
It was cool. We had our own little physics study group where everyone else is coming in. To be totally honest, because you couldn't do it on your own, like someone came to do it. Because it was like 3 hours of working on homework, 2 hours working on homework, 3 just looking around and stuff.
Sent you a friend request and you haven't accepted it.
What? I just did.
You did?
Yeah, I have my phone on airplane mode. Don't be like that, Luke. I'm trying to save my battery. I got an Android. I got one of those smartphones like them iPhones.
About how I have an Android too, and I keep it on airplane mode all the time.
Exactly. Like I got LG booster. I ain't trying to waste my battery the whole day. I'm trying to see spend it throughout the day because the exit got a long day. Like,
really, people?
I'm having on every mode during class. Like, so then I can listen to music while I'm practicing up and doing my what? Oh no.
I just got my airplane mode.
Yeah, like on airplane mode. Yeah, it's Android. Turn. Quit.
All you have to do is just.
Yeah, you just scroll.
Yeah, no, turn it off. It takes so much longer. You need to wait for the battery.
You have a what? Is that?
I need that too.
If you didn't get it,
Okay.
there were a lot of people who didn't get it. Yes, ma'am.
It sounds like those are saying for a change button.
Okay.
That's not like if I did it, that would break. It's not dropping.
Yeah, I'm going to pass this out in a second.
But it's got.
Oh, you
Wait till we get to our room. I'm gonna be
if you
so
drop
happy.
that without the case, it'll break.
Hey,
So I'm over there.
I got you.
No matter what, it doesn't go on the internet. So we're at so many people that right when I got it.
Okay. There were solutions for the test, and I put them here, and I think at least twice. But a lot of people didn't get solutions to the test. So if you didn't get a solution, please come get it.
That's like a cheat sheet. Could have given us this before the test. That would have been helpful.
No, that wouldn't have been helpful. You wouldn't have learned. Also, I passed out a solution for the worksheet on vectors. In the cross product section, I only had solutions involving determinant, and not everybody here knows how to use determinant. So I extended that now. So I'm passing this out. This is the problems involving cross products on the worksheet for vectors. The solution now has with and without determinants, so you can do it both ways.
What does determinants mean? The little.
I'll go. Yes, sir.
Oh, those.
I'll go over that. So I'm going to put this here as well. Everybody should grab a copy of that if you're wanting to know how that works. I'll go over determinants right now.
And you said with the cosines one you made there with the thing? With the AB?
The figure, yes. That was the law of cosines. The figure has an error in the, which I'll send out a correction for us. It's just the name for the angle is not correct in the figure. Okay, let's see here. Let me see why is this not doing what I want it to do? Hello. Stop.
Let's see. Dr. Dahl.
Just a second. No. What the heck?
Listen, is 9/11 now an official holiday? Well, it's not a holiday, but Remembrance Day?
What is going on with this?
I mean, it has, but like an official thing. Like
Yeah, it's actually on the calendar now.
It's always been on the calendar.
Yeah, ever since 2000 and
1.
Yeah. So it's just September 12th, 2001 is good on the calendar.
It's, you would say it again?
September 12th, the day after. Come on, Jacob, you know.
Okay.
You know.
Okay.
Hey, your face is red. What happened?
Dude, my face is always red.
I mean, I think it's just the lighting.
What?
What is it? It's not working the way it should.
I don't know.
Your hair is.
This is getting me nervous here.
No.
They came in and fixed my computer so it doesn't work anymore. Oh dear.
Oh, well, you can just let us know now.
Good. Okay, let you out of this. Okay, it's not working well, but I can still manage to do something. This is annoying. It's worse than it was. Okay, the determinant, just in case you didn't know what a determinant is, let me review here. A determinant is used in linear algebra, and it's shorthand notation for something. For example, you can have a determinant which is of a 2 by 2 matrix written like that. The determinant is first you take. I need to learn how to do it with the pointer, so let me try to do it with the pointer here. Can you see the pointer there? Yeah. So we have an A and a D, the diagonal elements of the matrix, and then the off-diagonal elements of the matrix. So the determinant is the product of the diagonal elements minus, oops. Oh, this is going to drive me nuts. This is really going to be the guy. You saw the guy in here who was fixing it for me. It's not working well. This is. Fortunately, I think what I'm planning to do today doesn't involve a lot of this, because this would really be bad. It's off. It's way off. Oh, I know what's wrong. I'll bet I have to recalibrate the thing. I didn't realize that. I have to do that beforehand. Good grief. Okay. Looks like I can't write. All right. I don't think I need to take the time to do this today, to fix it today. But okay, that's a 2 by 2 determinant. This is when I wish I had a blackboard. The 2 by 2 determinant is defined as the product like that. The product of the diagonal elements subtract the product of the off-diagonal elements. A 3 by 3 determinant, it's exactly off. Okay, given that, I can learn how to do this, I think. It's off by like a quarter of an inch. So if I write off, all right. You'll get a 3 by 3 determinant involving vectors, cross product, where the first line here represents the components of the first vector, and the second line represents the components of the second vector, and taking the cross product between them. This is in equation 218, I think, when he writes out the components of the cross product. So you can memorize what's in equation 218. Somebody have a little candy? Pull up equation 218 to make sure that it's correct, that I'm speaking of the right equation. I don't know the page. Equation 218. I just want to be sure I'm speaking of the right one. It's right here. 214. Excuse me. 214. The cross product is written in equation 214. The beginning of it just writes out all the elements. Yeah. Then he says it's equal to this determinant. And for those of you who know what the determinant is, it may be helpful. If you don't know what a determinant is, it's not very helpful. You don't need it. Don't worry about it, but I'll just mention it here in class in case you want to learn about it. So the determinant works like this. You take the one that's in the upper left-hand corner, x hat, and you write it in multiply it by the determinant formed by the other elements. So you cross out this row and that column and take that little 2 by 2 determinant right there. So this would be B, C, E, F. Then you have the determinant involving the next element on the top, y hat. You cross out this row and column and you have a 2 by 2 with what's left over, A, C, D, F. Okay. Notice the sign change. alternating sign here. And then, now the third element, you alternate sign again, which means it's now plus. Good grief, it's way all over the map. It's not even predictable. Okay, that's a Z. This is really frustrating. I mean, I'm a full 2 inches to the right of where it shows up on the screen here. And then you cross out the row and column, and it's this 2 by 2 determinant. I'll tell you what I'm going to do. I'm also going to write this up and print it out, because this is impossible here to draw anything that's intelligible on the screen. It's ridiculous. That was not helpful. Okay. All right, so then you use the 2 by 2 determinant to get the rest of it. Okay. So all that's happening in equation 214 is he's written it all out for you, and then he shows you the shorthand using the determinant, and they just really mean the same thing. Okay. So the determinant is a shorthand way to work out cross products. If you don't know that, just memorize the first part of equation 214. That's what you got to have, and then you can work out all the cross products in terms of components. Is that clear what I'm saying? And I'll write this down, pass it out on Monday, so you'll have it. Okay? And I apologize for this. Okay. So today we're beginning in the reading, we're beginning the second part of chapter 2. And let me back up a step, give you a bit of an overview on the book here. Remember the reason he's doing math here. Why? Quantity. Basic property, primal property of changeable things. Quantity. Have extension, parts outside of each other. So the mathematics is the study of quantity. And so it kind of makes sense to put it here. The difficulty pedagogically is some of this stuff we won't use until later in the book. Polar coordinates, you will note, I skipped over polar coordinates in chapter 2 in the assigned reading. Happy if you want to read it. We would not use polar coordinates until chapter 8. And so I just made a decision, we'll come back to chapter 2 when we get to chapter 8. We'll study polar coordinates then, rather than having you do it now and then you have to, what in the world was that 6 chapters ago? So we're going to do it that way. I could do that with other parts of the book. Cross product we don't actually get to until chapter 7. So dot product we get to almost immediately. But cross product is to chapter 7. The only reason I kept it together is because actually learning cross product kind of helps to learn the dot product, because there's a relationship between them. They're very similar. And they're different. So the difference helps to learn the dot product. Pedagogical choice, maybe next year I'll do it in a different order. But we really haven't gotten to the meat of the subject yet, which is going to be dynamics, locomotion, stuff moving, right? We haven't gotten to that yet. Just in very general terms, talk about change, things like that. So be patient here. I know some people at the end of chapter 2, they're thinking, what in the world, when are we ever going to get to something here I can figure it out? And the other thing to realize, of course, is that the mathematics comes out of the study of the physical. And you'll really see that connection. Once we get into physical things, you'll see the connection to the math that's coming now. Now we're studying it as mathematical things. So it's a little more abstract. The connection to the physical will be more understandable when we get there. So it is a bit of a pedagogical choice to do all this math right in chapter 2. And then you start seeing how it's connected to the physical, because of course it comes out of the physical. You'll see the connection better as we go. So be patient in that sense with yourself. If you don't quite see the physical connection, it'll come. It'll all be there. Okay, so the next subject in part B of chapter 2 is on calculus. And I'm going to give you a little bit of historical background. It gives you a bit of it here, but not really enough to get a sense of what's going on that I think is really important for you. So I'm going to try to write something up here. We'll see if it just maybe just get frustrated trying to write, but let's see. So this involves all of this mathematics, especially in the calculus, I'm going to invent a word. I just close my eyes and I'll do better. Don't pay attention to what I see because it's not connected to what I'm writing. Algebraification of geometry. Prior to the time of Descartes, it wasn't just Descartes, there were other people developing algebra. But really, algebra came into its own at that time, and Descartes was a primary player in the development of algebra. So in algebra, we take, for example, symbols. We have an X to represent what? What does a symbol like X represent? A number. And we might add it to y. So we might do something like that, like this: x squared minus y squared equals x plus y times x minus y. And this is an algebraic relation that is true for any pair of numbers x and y. Right? But notice what we've done here. We've done a bunch of things in this. We've written down an equation. We've got, first of all, symbols that point to some number, but it's not a specific number. It's a generic number. Two generic numbers here. And then we write down a numerical equality between two expressions. We say it's true, that is, they're numerically equal to each other for all values of x and y. That nobody had done before. That was new. No math had been done prior to that time like this. What was math like before? Okay, so hundreds of years prior to that time, the most advanced mathematics was developed by Euclid based on geometry. So edge and geometry was, I think, obviously came out of the need to build a building. And so you have straight edge and you have compass. You have this, you can take a string and you can mark out an arc from this point. And you want to make sure the building goes up straight and isn't leaning like this and that it's kind of square base or something, right? You want the angles to be right angles. So the need to be able to do this comes in construction. You can see how now you start thinking about it as an abstraction. Well, you know, you've got a line here and you want to draw the perpendicular to that line. How do you bisect the line? You have 2 points in between. You have a line. A and B, the 2 endpoints of a line. And I want to find the midpoint that's right between the two. How do I go about doing that? The tools that I have, edge and a compass. So how do I go about doing that? That's Euclid. And in fact, he is beautiful. You've probably studied a little bit of Euclid's geometry. One aspect of it is in deductive proofs. And so in high school they teach just a little section of that where you do side, angle, side, angle, proving the two triangles are congruent or things like that, right? It's a shame that we don't study that more because it's a really an elegant introduction to deductive reasoning. It's really a shame that we don't do more of that. You know, we get to college and they start talking about critical thinking. If they had done deductive reasoning in high school, the critical thinking would be a lot easier. But we don't have that anymore. Not much. Okay, so Euclid writes a big, thick book called The Elements, where he begins with very simple things. Points and lines. He starts with elements, like point, and he just gives a definition here, which is supposed to be something that everybody can understand. A point is that which has no part. It's just very small. It's got no size to it. So already we're talking about a mathematical thing, right? Because no physical thing is like this. A line is breadth less length. It's length with no width to it. The end of a line are points. The ends of a line are points. So he starts off with basic elements: point, line, arcs, those sorts of things. Oh, really? Let's see if I can get back to this again. Good. Okay. Oh, pointer. This is going to be frustrating here. Okay. How did I... okay. All right, I can still do it. Okay, so then he uses straight lines and points and things. He's going to figure out how to do various things. These are postulates. So let me go down to one that maybe you're familiar with. These are start off really simple. To construct an equilateral triangle on a given finite straight line is one. Let's look at this. And these have Java scripts. It's nice. This is a website from Clark University. And this is a nice little Java thing. And you can, if it were working as a Java thing. All right, it doesn't have Java installed on this. Boy, this is a real flub today, isn't it? Okay. Anyway, the Java allows you to distort, take those 2 points, A and B, move them around. What does he do? He takes an arc, takes a compass, put one in here, and make an arc starting at B and draw a circle around A with that radius, and then do the same thing around B. Where those 2 circles intersect, C is the third point. You draw you can draw the triangle between those 3 points. You get an equilateral triangle. Right? It's really easy to see why that works. That kind of stuff, straight edge and compass. So he goes from there, and he even gets to the point where at the end of the book, he's proving with straight edge and compass that square root of 2 is an irrational number. That's fantastic. How would you go about doing that, right? This is long before algebra. He calls it, the word is incommensurate that they use. Straight edge and compass, how would you go about proving that square root of 2 is irrational? Tough, isn't it? I mean, it's brilliant. It's fantastic stuff. It's amazing. I highly recommend that you study this.
It might show the thing if you click the little thing across the bottom, install.
Pardon?
The little install button.
Yeah, there we go. Okay. Oh, active X control. It's not going to let me install it.
Oh,
probably not. But I don't want to take the time.
Okay.
Just a short, quick anecdote that this reminds me of. I was debating with my dad over the fact how the old Greek philosophers and mathematicians were well versed in both reading and with math. And he made the argument that things were so much generic back then, they weren't as well defined. That I bring up the point, knowing how to do something and inventing how to do something are very different things.
I would even go back to that, the difference between well-defined and generic. Those are not opposites. Specific and generic are opposites. Well-defined and confused are opposites. But generic doesn't need to be confused. Right? Generic can be precise, but it is generic and not specific. The modern mindset is, I think, and I'm trying to get you away from thinking in those terms, specific is somehow well-defined because it's specific. But I'm trying to broaden the way you think so that generic is indeed more abstract, but it actually can be very well-defined. Okay. Triangle is abstract, but it can be very precisely defined. But it's not a particular triangle. Right? Okay. So, this is mathematics for hundreds of years, this kind of stuff. Even Galileo and Newton have a lot of this stuff in their notebooks. They're doing all of their proofs and their demonstrations, their discussions, they look like they were taken from the pages of Euclid because they have all these sorts of constructions, geometrical constructions. Up till the time of Descartes, Descartes makes the following step, which is profound. And it's worth you thinking about this, because we do this, you've learned this in your math courses without thinking about it, without being told where it comes from or why it is the way it is. So Euclid does Descartes does the following thing. I'm going to go back to, I'm going to compare geometry, which is straight edge and compass kind of stuff. And then, man, this is really going to be frustrating here. Hold on. I apologize for this. So this is going to be mapping to algebra, in other words, called analytical geometry. It's the algebraic geometry, the algebraification of geometry. So remember, Euclid starts with a point. That's one of the things that you start with when you're studying geometrical objects, the mathematical concept of a point that has no size. What does Descartes do to a point? Well, he says, all right, if there's a point there, we're going to have coordinates, y and x. And so we're going to speak of a point. This is really awful. There we go. We're going to speak of a point as a pair of numbers, x and y, the coordinates we would call it. That's the Cartesian coordinate system, right? We named it after him. He's the one who really helped us to understand what it was about, how to do it. So he's transferred a point to a pair of numbers. A pair of numbers is not a point, right? Isn't that clear? That a point is not a pair of numbers, and a pair of numbers is not a point. They're not the same thing at all. But he's going to draw a correspondence between them. Okay, now, what about an equation? In algebra, we have lots of equations. How about, let's go back to the geometrical thing first. How about a line? Remember, that was another thing he talked about. A line is something with a breadthless width, a breadthless length, something with no width to it. A line. What's a line? If you think of it algebraically, it's a relation between those two numbers, x and y. In fact, we could write down an equation which is y equals ax plus b. I can't fix it because it'll end up some bizarre place if I go back and try to fix that a. Ax plus b. A line is not an equation. An equation is not a line, but we've made a correspondence between them. So this is the algebraic representation. It's a relationship between the coordinates x and y all along a line where every point on that has been represented as a pair of points, and now we have a relation between them. So now we've taken a line and turned it into an equation, a particular kind of an equation. It's called what kind of equation is that?
Linear.
Right, linear equation. Why do we call it a linear equation? Because it corresponds to a straight line, right? But that is not a line. That's an equation. It's a relation between numbers. And that's not an equation. It's a line. But you see this, if you haven't stopped to think about this, you might have gone past this without ever realizing, wow, this is really kind of profound, what we've got here. All of these steps, symbolization, equations, the line, I mean, it's all rather surprising. And it's not at all obvious, because it took us hundreds of years to go from the point of doing Euclid, who was brilliant. He never even got to this point of writing these sorts of algebraic relations down. Okay, how about another curve? Let's do a parabola. How about that one? A parabola. Well, it's another ax squared. Okay, it's another relation. A quadratic. We don't call it parabolic equation. Maybe we do, but we have a linear equation. But this is called a quadratic. Lots of them. A circle. Let's do a circle. No, don't do that. Undo delete page, thank you. Let me have another one. Okay, so how about another one? Let's see, we were doing the shapes over here, right? A circle. Square plus y squared equals 1, or the square of the radius. It's another special equation. It relates the points on the circle. We can take all kinds of shapes. This is like a trig function, nothing different. Cosine x could be that. A wave like that could be a cosine function. Other functions, right? So we've got this relationship between equations and shapes. That's the algebraification of geometry. So I can take all of the proofs in Euclid that were done with straight edge and compass, but now I do something different with them. I manipulate symbols. If I want to solve this for y, what do I do?
Subtract x squared and x squared.
Right. Or I could use the quadratic equation, right? The solution for a quadratic equation, right? Oh, no, I'm sorry, not that one. It have to be the one above it, right? Y equals ax squared. If I could have, if y is equal to ax squared plus bx plus c, and I want to find where the curve crosses the axis, I've solved for the quadratic equation. You can see, what do I do with the algebra? I manipulate symbols. fact, I have a program on the computer. Has anybody used Maple or Mathematica? I'll bring it in one day and show it to you. It's simply a symbolic manipulator. It just does the algebra. There are no numbers. It's just symbols that it manipulates, and it solves quadratic equations or more complicated equations. It just manipulates symbols. So there's a way to solve these. It's an algorithmic approach to solving algebra. Okay. So this is really profound here, but it's still all math. But mathematics from that point forward completely transforms. The mathematics that follows Descartes is completely unlike, it's almost unrecognizable. Tremendous progress from that point forward. Whereas the work prior to that there was progress, but it was very slow. And that's because you could take things like prove that 2, square root of 2 is irrational. It becomes an algebraic proof, and it's really simple. I can do it in 3 lines. It's quite easy. So it's amazing what you can do with this algebra. It's fantastic stuff. But what's it got to do with physics? Well, remember these shapes come from quantity, so there's a connection. Here's the connection. Let's suppose I have an object. I don't want to drop anything breakable. But I want to drop here. I'll drop a pencil. It's not very big, but you can understand. Okay. All right. Now, and this was done by the Oxford calculators, for example, those people in the 13th century. I'm going to wait a beat. I'm going to drop it, wait a beat, see how far it's fallen. And I'm going to wait 2 beats and see how far it's fallen. So what I'm going to do is I'm going to measure the distance it's fallen at different times. And I'm going to make a plot of that. How far does it fall as a function of time? And let's see if I can plot here. I might not be able to do it. This is the measure of time here. Okay. It's going to look like what kind of curve? I'm going to have lots of points along here. I'm going to have points, a point here, a point here, a point here, a point here, a point here. Lots of points on there, and I connect them by a smooth curve. You do this in physics lab, something like that. Make a bunch of points, different positions at different times, connect with a curve. What kind of curve do you get? It's a parabola. Right? This was one of the big discoveries of the 13th century. If I plot the distance at different times, and I get a curve. Now that is not a changing object. It's static. It's a static representation of a bunch of measurements which are done at different times on something that's changing, which is falling. But there's nothing like this in here. There's no parabola in this pencil. Right? It's not in here. This thing falling is a physical thing that's changing, and then I look at it at different times, and then I capture some quantitative aspect of that, which is how far it's fallen at different times, and I get a shape. Bingo! Shape. So now I've gone from physical changing thing to shapes, geometry. That's step 1. It's amazing. Right? That's not a changing thing. It's just a shape. Let's think about what other shapes we might have. If I were to do the same thing for something which is standing still and it's not moving, and I measure its distance from the end, what is this plot going to look like? If I measure the position of this pencil now, I measure it again, I measure it again, I measure it again, and I plot it on this curve. What's it going to look like? A horizontal line. Straight line. With no slope. What if I roll the ball and I do the same measurement? What's that going to look like? If I get it to roll without friction.
Line with a slope.
Yeah, line with a slope. Could be positive, could be negative, straight line. Now and then the thing that's falling is a parabola. And let's hang a mass on the end of a spring and have it oscillate like this. It's going to be a cosine, a sine wave. Every one of these special cases that I've done of motion, I can map onto a shape. And now Descartes allows me to map it to an equation. And bingo, I've now got algebra that I can use to describe motion. Calculus, here it is. It just appeared in front of you, right? So what is the calculus? Well, first you start with shapes. So there's that step which isn't talked about, is how, just that step. It's very simple, but who stops to tell you and get you to think about what you've done here, to take a series of measurements and then draw a line through it to make a shape. Now a straight line or a curve or something else. Okay, so now what can we do with that? Well, it's very, very interesting. One of the exercises in the analytical geometry is to take a curve which represents some function. All right, and now what I want to do, oh boy, this is going to be a challenge. Let's see if I can do this. I want to draw, it almost worked. All right, that should be tangent, it should touch. It's a straight line that touches the curve only at one point. That's a tangent. Okay, and I want to know, well, what is the slope of that curve, the straight line that touches the curve at some point? Just like I could compare the slopes of these different lines. This slope, this has no slope, this has a positive slope, this has a negative slope. Another one might be really slopey, you know. So I want to look at slopiness of that thing. So down here it's going to have no slope. As I wait further, the tangent's going to be slopier as I get farther out. So how do I relate the slope to where it crosses the curve here? Because remember, at each point here, I'm going to have, oh, I wonder if I could use this. This might be better. Okay, that's better than the stylus. Good. Okay, so this is some x where the tangent touches the curve. Right? So what I want to know is, what is the slope of the tangent that touches the curve at that point? And the calculus tells you the slope of that is y prime of x above, which is 2x in this case. Oh, man. This is really bad. I'm sorry for doing this. And I can't do it all with this. I could try it. I'll try it with this. Y prime of x equals 2x. That's the value of the slope of the tangent that touches the curve x squared at the point x. And that's what we're wanting to do with this algebra, this now calculus, which is find the slope. And that's all the calculus is for that part of it. There's two parts. There's the derivatives and there's the integration. We haven't told you about the integrals yet. That's coming. But that's all that the derivative is. The slope of the tangent to the curve that touches the curve at some point x. Now notice what I've done. I've got a new function. I had this function, I have a new function. I'll show you how to go from one to the other. We'll talk about that. It's coming here. But what happens here, I have a function, and I get a new function. Because the slope is changing with x. Where it touches the curve is x, and there's a different slope at each different place. So I have a new function, 2x. So I've gone from one function to another function. So I've got now a way of transforming from one function to another function. So I have two functions. One represents the original curve, and now I could plot a new curve, which is, some people would say, is the derivative of the other curve. So I have two curves. This curve would be a straight line, right? Okay. Okay, so let's see exactly how this works then. We make some measurements of how far it's dropped with respect to time. Notice something has happened when I make that comparison. I'm going to make this plot of how far it drops as a function of time. So this is how far it drops. And it's going to be a parabola like this. Now, notice one thing here. Time has appeared, whereas before we just had distance. We'd have one distance compared to another distance. Now we've got time on that. Why? How can we put time on this axis? How could that happen?
We quantified time.
Exactly. We measured it, produced a number. Has time been essentially reduced to quantity?
Yeah.
No. Can't do it. Right? Why can't you do it? Time is not essentially quantity. It's a different sort of thing. But we've done, by analogy to number, this measurement process, we have produced something that looks like quantity. It's a number. But time is, in essence, not position. Time and space are not the same thing. I can go backwards and forth in space. I can't go back and forth in time. That's an easy demonstration right there of the difference in character between the two. Right? I can do this in space. I can't do it in time. So even though I've got this thing, I can't go back and forth in time, whereas this object can go up and down. All right? So it looks like space. It isn't space. I've quantified time, but it isn't essentially space. There is an essential difference between space and time. But I plot it like that, and I might be tempted to mistake one for the other. I might start thinking that time and space are the same. Not the first person to make that mistake, right? If I did that. But it isn't the same. And if you understand this process of measurement and symbolization, drawing plots and curves and stuff, now you're starting to see what could happen if you get wrapped up in the quantifiable and think that that's all there is the imperiometric. Then you could lose sight of what's really going on. And you could say things that look like time and space are the same. They're not. Okay, so let's do this. Let's suppose I want to calculate the tangent to this curve. Okay, so to calculate the tangent to the curve, here's what I'm going to draw a straight line that actually intersects the curve at two places. And this is done carefully in the book with exactly the same function. Right? I'm going to draw at 1 time t, or I could do it for x. Doesn't matter whether I've got x or time, right? I've kind of merged them to look the same at this point. So I could do this with x, and I go from x to x plus delta x, or I could do it with time, t plus delta t. The book starts off by doing it with x, just to make it clear that this is a mathematical, geometrical sort of thing. And then he does it again in a couple of pages with time. And if you aren't paying attention, he's waving his hands here. Look, this is an important step. This is not obvious that I can replace the space, the position, with the time. So, but here it is. So it crosses the curve at intersects the curve at 2 points. Now, if I shorten the time interval, I could draw a straight line here. I'm going to shorten the time interval. Delta t is less. And then I'm going to keep shrinking delta t, hold this one fixed, and I keep shrinking this. At how many locations does this straight line intersect that curve? It's always twice. And if I shorten the time, how many places does it intersect the curve? It's always 2. That doesn't change. But I've got this thing, this curve, which is approaching a tangent, and how many places does the tangent cross the curve? Once. But this approximation to the tangent is always 2. Okay, but the slope of this line is approaching the slope of the tangent. And this is the process called limit. I'm going to take smaller and smaller steps, delta t, until I get something that's arbitrarily closer and closer, as close as I like, to the tangent, so that it has the slope of the tangent. So let's see how that works. Okay, so the difference, I have h of t plus delta t. That's the value at the second the place where it crosses at the top. at minus h of t. That's the difference in h here. That's this interval between here and here. Okay, that's the difference in h. And now if I divide, that's the rise, and I'm going to divide by the run. Oops, I'd rather have black here. I'm going to divide by the run. That's the slope. I take that difference, and I want to do it for smaller and smaller times. And that's this idea of taking a limit. Now, it goes to 0. The actual limit, is it a real being or a being of reason? Being of reason. Any completed infinity is a being of reason. It's just only in the mind, not in the world. This is all constructing beings of reason associated with another being of reason, which is this curve, which is the result of having plotted these things. I have this curve that's up in the mind. Really, it's not. There's no curve in this thing, right? There's no parabola in this thing when it falls. Okay, I do this, and let's look at the function h. I said it was quadratic, square in time. So we have, let's see, t plus delta t squared minus t squared over delta t. And if we expand out the binomial, then we have t squared plus 2 delta t plus delta t squared. We subtract off the t squared, so this is then going to be equal to, take another limit here, we have 2t delta t plus delta t squared all over delta t. So this equals 2t plus delta t.
How did you get rid of the h?
H is, I said, was a quadratic function. Let's suppose that h is a quadratic function, just to give us something, and it corresponds to what's happening for this pencil dropping. It is a quadratic function. So in that case, now I have a number 2t plus delta t, and I want to take delta t smaller and smaller. And so if I take delta t smaller and smaller, I'll end up with just 2t, right? If delta t gets smaller and smaller. So in that limit, having done the limit correctly, just gives me 2t. So the derivative of t squared is 2t. That means the slope of the curve, the slope of the line that touches the curve at t, the slope of that is 2t. So I've taken one function, t squared produced another function, 2t, and I could plot the other function. So the new function, if I plotted it, would be 2t. And so that function would correspond to the original function, and the relationship is that it's a derivative, and this is 2t here, where the first function was t squared. So I've got a new curve. I've taken one curve, produced another curve. I've gotten one function and produced another function, because they go together. Equations and functions correspond to each other. All right, I could do another derivative here, but the slope is always the same here. The slope of the tangent here, the tangent goes through that function because it's a linear function, right? So the derivative of this would be 2. The slope of that curve is 2 everywhere. It doesn't depend on t. Okay, so that, you see how far we've gone in this process from taking straight edge and compass and drawing things and bisecting angles, drawing arcs and stuff, and then we go to this stuff where we're manipulating algebraic symbols. If you don't see that connection, so there are those of us who are good at this and those of us who are not so good at this. The ones that are really good at manipulating symbols is what I mean. We're all good at understanding the physical in some sense because we live it. But some of us, that's not a natural thing to write down symbols and to take derivatives. Speaking is natural. Hearing is natural. Reading is not a natural thing, which is why it takes so long for us to learn how to do it. Walking is natural. We do it within a year. And we start speaking shortly after, right? These are natural things. Reading is not a natural thing. Writing is not a natural thing. Putting words down as symbols is not a natural thing. It's not something that comes naturally to us. We have to learn how to do it. We have to be taught how. The symbolization process, in that sense, is not natural to us, but it represents something in our mind that is natural to us, which is an abstraction. Abstraction is natural to us. And so it's natural, in that sense, it's kind of not surprising that we express abstract things symbolically. because they represent abstract things. Okay, but there are those of us who are good at that. You can do the recipe. How do you solve a quadratic equation? Minus b plus or minus square root of b squared minus 4ac over 2a, right? That's a recipe. A computer can do that. But there's the other part. There are the other students who are not good at doing the symbols because they don't really quite understand that step. That there's this something under the symbolization process never quite clicks for them. Just like for some people, reading is really tough. Never quite clicks. Maybe they get better at it if they work hard at it. They can overcome with special training, maybe. So the same thing happens with some people. The symbolization is easy, and this group not so easy. Both groups, neither group is really taught what it all means. These people who are good at turning the crank. Oh, you're good at this. You get an A in the course, go on to the next more advanced course, right? So you get more complicated equations to solve with symbols and stuff, and it just gets more and more sophisticated, more and more complicated. This group says, that's science, I can't stand that stuff, I don't understand, it doesn't make any sense to me because it's all equational. And they get a very bad impression of science because they think, ugh, those people think differently somehow. Right? Try to have a conversation with somebody, you tell them you're a physics major. That'd kill the conversation, won't it? You must be really smart or something, right? They don't, because probably they don't understand this equational stuff. That's what it is that they don't understand. They're one of this group that has a hard time with the symbolization that doesn't really connect with them. So there's this gap that's there. But neither group really understands what it is that they're doing. The first group is good and wants to express things in terms of the symbols. What do? Well, I manipulate equations, you know. That's not physics, really, but that's kind of what it comes down to in the standard way of doing things and understanding it. Right? Okay, so this, I would suspect, is probably the first time you've recognized these things. So this step here, going up here, I've got a tangent to the position versus time plot. I have the slope of that tangent. Now, what's the name of that thing? We call it speed. Not quite right. Speed is not the slope of the tangent to the position versus time curve. Speed is the rate of change of place. Right? This thing has a speed, or there's a speed associated with the change, a rate of change. That's speed. But we've made this analogy to the slope of the tangent, to the position versus time plot. You see this subtle thing that we've swapped it over. And you could end up thinking that that is speed. The slope of that is the speed. And they'll say that in most courses in physics. That's the speed. The slope of this curve is the speed. It's analogous to the speed. In this sense, now you should be able to understand the analogy. We're making a quantitative analogy all over the place, right? We're measuring the location, quantifying that. Measuring the time, quantifying that. We're making this curve, quantifying that. Everything's been quantified. Okay, so it's an analogy. But it doesn't capture the thing in its essence. It only captures some aspect, which is the quantitative aspect of the thing. Okay, this is extremely powerful, though, because we can do all sorts of things we weren't able to do before with great ease. Algebra is so much easier than doing the straight edge and compass. I can do all kinds of stuff with algebra that I